I'll start even by doing a very short disclaimer that my presentation will not have, I'll say, the same technical depth as the ones I've seen so far. But fortunately, also right after my presentation, we'll have Bart van der Laar from TNO, who will cover also a few of the developments we did together. And I believe that will be also very, very exciting, Bart. But I would say we are all here today because I think we all believe that optical wireless communication can indeed overcome many of the current technical challenges. But by doing so, it can also overcome challenges of the society as a whole. And this is where I'll start my presentation because right now, we all know connectivity enables prosperity, but at this moment, in both European Union as well as, I'll say, the rest of the world, we are still not meeting the standards, the needs for connectivity. And if you think about the European Commission goal of reaching 100 megabits per second networks just by 2025, we are far from that. And it's exactly the same in the US, where there are still bills of $1 billion being approved to indeed reach these connectivity goals. But even besides all we are the lucky ones. We are in the most developed countries in the world. And out there are still more than 40% of people in the world that don't have access to internet at all. And this is data from the UNESCO. And why? So fiber optics is fantastic. It provides ultra high bandwidth over long range and ultra high reliability. This is the backbone of, I would say, any communications network of today. However, it takes a long time to deploy. And in order to meet the goals I just mentioned in the previous slide, we'll need a lot more time, a lot more, I would say even more than a decade or decades to connect the world. And besides that, it's quite capital intensive. It requires a lot of investment, it's capital intensive, and it's often not a technical or economically viable solution for addressing issues such as the last mile or connecting rural areas. The alternative is obviously to go wireless. And currently, telecom operators are investing in what is called the E-band, so bands between 60 and 80 gigahertz. And E-band has also quite a lot of advantages. It can provide higher bandwidth than the previous existing radio solutions. It's obviously also a wireless standard. So everyone is used to use radio in their telecom networks. And it's quite easy to deploy if we think about a comparison to fiber optics. However, and I think this has also been addressed today, there are quite some disadvantages when you use radio frequency. And first of all, this is regulated spectrum. So any company that wants to transmit over certain bands of the spectrum, they require a license from the government, as well as when we start using more and more radio frequency devices, which we are now reaching at billions of radio devices all over the world, there is also an issue with interference. And when devices start to affect each other, this results also in a very high power usage. So a lot of devices being installed all over the world. But I would say the biggest limit, specifically of E-band, that it has a big trade-off in radio. It has a big trade-off between bandwidth and range. And when we start using higher and higher frequencies of the spectrum, then the range of each of the devices is getting shorter and shorter. So for E-band to transmit data rates above 10 gigabit per second, then the distances that it can cover are only up to about 2 kilometers or 2.5 kilometers. So if you look at the broadband space, there is an obvious need for high bandwidth systems that can transmit over those distances over 2 and 2.5 kilometers. By doing so, obviously in rural areas and suburban areas, the need for this distance is even clearer. But that's exactly the same as a new or a more recent case. And when we talk about enterprise networks, there is also a need for these ultra high bandwidth systems that can be deployed quickly. But in addition is, here it's also important, the security of the networks. I'll say finally, there are also needs for, in terms of rapid deployability, devices that can be quickly set up, and again, that can transmit at this high speed and high speed rates, as well as over longer distances. So, in a summary, there are at least 3 segments in the telecom industry where there is clear need for high bandwidth and long distance solutions that rely and that have the basis on a similar or same product. This is where we see that free space optics can play a role, and in general, free space optics promises the capability, the potential to achieve these very high bit rates over very long ranges, but also a few others as lower latency, higher security of the links, higher efficiency, which all of them result in a lower total cost of ownership for the telecom operators. How is this done generically? Free space optics can achieve higher bit rate just simply because of the higher bandwidth used. It can achieve longer range because of the directivity. It has much higher directivity than radio. Lower latency if we compare to fiber. Obviously, most of the fiber connections are not a straight line, while in free space optics, we use a direct line of sight. But also in terms of the speed, compared to fiber, we obviously don't have the glass that causes about 30% lower speed. In terms of higher security when compared to radio, it's way less detectable. This is also because of the directivity of the beam. And I'll say finally, higher efficiency, especially when we think about the power efficiency, which results again in the lower total cost of ownership because of the need for less repeaters. That's why, and I believe there will be many other presentations also about the use of free space optics in space in the long range, but these companies and all these projects are using FSO because of this high bit rate capability over this long distance. Now, where does Aircision enter in all of this? So Aircision goal is to bring these space-grade technologies being developed over the last, say, decade, from space down to planet Earth. And by, obviously, the challenges are quite different. The space is quite different and has quite different requirements from terrestrial applications. Nevertheless, our goal is to achieve bit rates of 100 gigabit per second or even higher, and long ranges between 5 to 10 kilometers. These are the 2 key goals. And how do we do this? So obviously, in order to achieve this long range, what do we call long range? Because space is obviously, we are talking about thousands of kilometers, but in terrestrial applications, a 10-kilometer system has already quite a considerable distance. And in order to do this, it's key to be capable of aligning these 2 devices over these distances. These devices will be installed in telecom towers or buildings, which obviously are affected by the twist and sway of the towers, natural earth movements, but then there will be also all kinds of atmospheric effects in the middle. Second part is, in order to achieve high bandwidth, is very straightforward. It's the importance of transmitting a lot more data on just single optical channels. And for this, the enabler is basically the use of faster modulators and data aggregators that can transmit at these higher speeds. These two, let's say, USPs result, as I mentioned before, in the lower total cost of ownership for the telecom operators. If we think about E-band systems that can, as I mentioned before, can reach about 2.5 kilometers, when we talk about minimum rates of 10 gigabit per second, then we will need a lot less repeaters in order to transmit the same kind of signal. So I talked about the twist and sway, so as well as the atmospheric effects. And these, I would say, are the main challenges in order to allow our photons to go from the origin to the endpoint. We estimate that the combination of all these mechanisms affecting the twists and sways lead up to about 3 degrees. And our system will have actually a higher performance than that, accommodating about 5 degrees. Also, when we talk about atmospheric effects, first ones that we think about are obviously rain and snow, which cause high power attenuation, and effects such as scattering and absorption by the light, absorption of the light, will have an impact in the link availability of the system. But when we look at this graph on the left side, and these are our own calculations based on weather data from the Schiphol airport in the Netherlands, and when comparing the link availability models for systems that can transmit at least 10 gigabits per second speeds, then we see that for E-band, it's actually even lower than the 2 kilometers I mentioned, while for a free space optical system, there is a tipping point there where after about 1.5, 1.6 kilometers, then the link availability of the system is higher than the E-band. On the right side, just we obviously talk with many of the telecom operators, which will are the ones that define the system requirements. And they have all mentioned that, yes, E-band has those limitations. Link availability, around 98% is enough to broadband use cases. And that, again, E-band is facing its challenges, but I would still say, and looking at the graph again on the left, E-band has for sure a higher link availability for shorter ranges. This all results in a lower total cost of ownership, and this is just to show in a very simplistic way, we need a lot less repeaters. So this will result in, again, higher power efficiency, less cost in terms of masts and towers. And when we think also about access to electricity, we will need a lot more access or a lot less access points in order to transmit all the data that we want. This is
Aircision and TNO partnered in 2020 with a mission to build high-performing free space optic systems.
We're going to see if we can transmit 10 gigabits per second over a distance of 2.5 kilometers from the Meteor Tower all the way to the TNO Tower.
This test will give our team valuable data and input for the development of our next generation systems.
Okay, this is it. 3, 2, 1.
I think we got it.
Nice.
We are very happy with the outcome of this test, and we believe that we achieved a very important milestone towards our goal of reaching the high bit rates and long distances.
So the next presentation, as I mentioned, and Bart is also here today, and we will deep dive also into more details of these tests that we conducted together. But as you can see in the video, there was it's quite a significant distance, and already 2.5. When you talk about 2.5 kilometers, it's hard to see the tower and on the next side with our human eyes. But this is clear that free space optics has now the opportunity to play a bigger role in the telecommunications market. And there are already plenty of estimations on the number of units that will be required and that will help in Europe, in the US, but also all over the world to connect the more households and more people. We are not doing this alone, and in order to get to these high bandwidth and long distance systems, we are building what we call the ground-to-ground ecosystem with space optics. And this is one of the challenges, I think mentioned also in previous presentations. One of the main challenges will be for sure the industrialization and bringing costs down in the production of such devices. We are part of a project called the NWO Perspective Program for optical wireless superhighways. I think many of the companies, organizations represented also at this conference are part of it. And the goal is obviously to research and to understand what are the capabilities in terms of beam steering, in terms of data transmission rates, modulators, detectors, and so on and so on and so on, that will allow all of us to bring these technologies to market. I'll say we have a fantastic team and covering all areas of the business, but on the technical side, we have people experienced in the semiconductor industry, optics, mechanics, electronics, and so on. It's quite important also to be surrounded by a group of people, advisors, that can help us in defining the requirements of the telecom industry, but also to make all the connections, relevant connections to the operators. Finally, and this is again coming back to the beginning, this is what drives us. And at Aircision, we strongly believe that by using optical wireless communication, we can improve telecom infrastructure. And by doing so, we can improve access to information, to education, and reduce what we call the digital divide in the world. And thank you. This is it. We are Aircision, and we are powering high-speed connected world.